This PCB has come to me for repair for the first time, and I don't know which IC is used in it or its number because the IC is completely blown. Therefore, there's no way for me to identify it or see its number. However, the IC's pins will make things a bit easier for me because when I draw the system later, it will help me figure out how to identify it. Fortunately, I have another PCB on hand, and since these PCBs commonly come for repair, I already know the typical faults they have and the components used at specific locations. I've studied this type of PCB extensively, so this makes it easier for me. Also, this is an older communication system, so it uses ICs that are standard for such systems. Now, looking at this PCB, its communication system is completely different. Let me explain it to you. The pink-colored wire here is the communication wire. Moving on, there is one optocoupler installed here, and another optocoupler is installed there. This means that its communication setup is also different, and the switching IC is different as well. One indication of this is that its chopper transformer is smaller compared to the larger chopper transformers usually seen in similar systems. The IC number commonly used in these PCBs is top 243PN, and I already have plenty of spare ones. I could try installing it here to test the system. However, the issue is that if I install it and the system doesn't work properly, if something else gets damaged after installing it, then this PCB will not be repairable. That's why I'll first study the circuit thoroughly. Let's analyze this IC. IC300 has all its pins joined, and it's connected to the negative terminal of the large capacitor here. This makes it clear that this is the IC's source. Now, if we check this pin, there's a TVS diode installed in the center. TVS diodes are typically connected to the drain terminal to protect against electrical surges. However, there are two more pins here, and they need to be understood. To do this, I'll examine the entire system. There's a TL431 installed, along with capacitors and diodes. I'll draw out the circuit to better understand how everything is connected. Let me share another observation with you. What I notice in this PCB, and what I believe should be present, is that there is no voltage regulator installed. This means that all the voltages are directly supplied from the chopper transformer to the system. If you look closely, there's no voltage regulator present in this system anywhere downstream. Now, you can see that I've removed several components from the PCB. For example, I've taken out the chopper transformer, and the switching IC was already removed earlier. Additionally, I've removed a capacitor. With these components removed, the PCB traces are now more visible, making it easier for me to create its schematic diagram. When I removed the chopper transformer, I observed that its low side has 5 pins, while the high side has 4 pins, and the 5th pin on the high side is missing. Here's the diagram I've drawn for the chopper transformer. I've labeled pins 1 to 4 on one side and similarly labeled the pins on the other side. As for the starting point, I've marked the IC, but since I don't yet know which switching IC it is, I've used a question mark to indicate it. Our goal is to identify the correct switching IC for this PCB. Now, moving forward with the tracing. At one point, I observed 320 volt DC coming in, with the DC negative connected to the source pin of the IC. The DC positive is directly connected to the chopper transformer. The role of the switching IC here is critical. It must activate the chopper transformer. Once the chopper is switched on, as I mentioned earlier, the capacitors downstream should generate the required voltages. If these voltages are successfully generated, the rest of the system will start functioning correctly. Take a look at capacitor C316. After studying it, I found that this part of the system connects to the compressor drive system, specifically the IPM, Intelligent Power Module. This means we should expect 15 volts at this point. Next, I studied the diode that leads to capacitor C314. At this capacitor, we should get 5 volts. These 5 volts are then routed to a voltage detector, which operates at 4.2 volts. For the voltage detector to operate effectively, it requires a minimum input of 4.2 DC volts. Unfortunately, the transformer is currently outputting only 4.1 DC volts. This deficit interrupts the voltage detector's ability to transmit voltage signals to the microcontroller, leading to a complete loss of signal or grounding it instead. When the microcontroller receives a ground signal from the voltage detector, it quickly shut down the PCB. Therefore, it is imperative that the voltage detector consistently monitors and ensures the proper generation of voltage. When this detector senses the required voltage, it supplies power to the rest of the system. Finally, for the third capacitor, C315, we should get 12 volts. These 12 volts are directly supplied to the ULN 2003 IC, which is used to control the switching relays. I've completed the schematic diagram for this PCB. In the diagram, I've included a reference IC, but I haven't drawn all its pins, just enough to provide an idea of what can be installed here. Now take a look at pin number 3. It's connected to a capacitor of 10 microfarads and 25 volts, which which indicates that the current and voltage limits are being set at this point. Additionally, the reference IC is shown supplying voltage to pin 4, which means feedback is being generated from here. This feedback allows the switching IC to operate correctly. The issue now is identifying the exact IC to use. Now, we have pin information to help us determine the number of switching ICs. This procedure is essential if you are trying to identify the number of blown ICs, as no other reliable or proven method is available. Based on our study and experience, along with observing the IC's installation location, we have determined the following. Pin 1 serves the feedback function. Pin 2 performs a multifunctional role related to boot functionality. Pin 3 is not present in the IC. Pin 4 is a drain pin. Pins 5 through 8 are source pins appropriately arranged from top to bottom. Now, we know the pins and understand their respective functions. We can use two different methods. The first method works like this. I have a box in front of me containing many switching ICs. Most of these switching IC is used in inverter mini-split air conditioner are in my working category. When I open it, I find many ICs with various numbers. You might think locating the required IC among so many would be challenging, but that's not the case. First, I categorize them systematically. Now, I separate the ICs based on physical appearance. 4 categories are separated here. This step significantly reduces confusion and makes the search process much more efficient. In the first category, you can see that their physical shape is entirely different from our required IC, so we set them aside. I have also separated the second category based on physical appearance. These are all ICs with 8 pins. We can't replace our required IC with any of these. At the moment, I have 9 to 10 different types of numbers available, which I have separated from the rest. The third category also has physical differences, but the variation is minor. For example, if we are not very experienced, we could consider fitting one of these ICs. However, let me show you how they are different. In this case, you can see that this IC has 7 pins and closely resembles our required IC. But if you observe, pin 1 is currently on the left side, and the 3-pin group on the right side is numbered 5, 7, and 8, which does not match our requirements and is incorrect. These are approximately 12 different types of numbers, which I have separated. Finally, these are the ICs, among which one might work for my purpose. I have also separated them based on their physical appearance. As you can see, most of these IC packets belong to the TNY family. This is another set of TNY family ICs, but with different numbers. Ultimately, the top 258 family IC also physically resembles our required IC. I have created a separate category that can be further divided. Based on my experience, I know that the IC units I currently possess, ranging from TNY274PN to TNY280, all belong to the same family. The only difference among them is their wattage. This approach will allow me to do even less work. This method requires only checking the datasheets for TNY274PN, TNY288PG, TNY176PG, top 258. It is reliable, especially when I am unsure about the IC pins and their functions. Although this procedure can be lengthy at times, it benefits me most of the time. Based on the system's requirements and capacity, you can choose any IC from the TNY274 to TNY280 series. Alternatively, you can also use an IC from the TNY174 to TN177 family, as they belong to the same category. You'll need to verify the system's capacity and select an IC accordingly to ensure proper functionality. To use the second method, open your computer or smartphone screen and launch the Chrome browser. In the browser, type remount-.net or select it if it appears in the suggestions. Click on this first link. The browser will navigate you to this website. This website is in Russian, so if you're unfamiliar with the language, click the pop-up option to change it to English. It's important to note that the second method is beneficial only if you already know all the pins and their respective functions. Otherwise, the first method remains a more reliable option. On this website, you'll see an image of the burned IC. Now, let's explore the interface of this page. You will notice 6 vertical boxes displayed. Each box contains numbers ranging from 1 to 10, and the function of the selected pin is written above each box. This website page is designed to help you identify 2 different types of SMPS ICs. Many of you may already know that some switching ICs have a built-in MOSFET, while in others, an external MOSFET is used. This website system has been created to accommodate both types of IC setups, allowing users to analyze and work effectively with either configuration. When you want to identify the number of an IC with a built-in MOSFET, you will input the IC's data into the first 4 or 5 boxes. On the other hand, the drive DRV box, along with the first 3 boxes and the 5th box, will be used when you need to identify the number of an external type IC. This approach ensures you enter the correct data depending on the type of IC you are working with. The next thing to explain is that if you have selected a box for a specific function and accidentally made the wrong selection, you want to assign the function of that pin to another box. You can press this button. By pressing it, all the boxes will be deselected, allowing you to easily select the pin for another box. In this way, the refresh button provided does not refresh just the boxes. Instead, the entire page is refreshed. At the beginning of the video, we identified the IC pins and their functions, and I provided you with the IC number. Now, we'll input that data here. If you've watched the entire video, you should know that this IC does not have a VCC pin, so that we will skip that box. Next, we will insert the ground pin into this box. As you may recall, this integrated circuit does not have a dedicated ground pin. Instead, it has a source pin. Therefore, among the 5 to 8 pins available, we will enter one of these pins into the ground box. Let's proceed by entering pin 5. Next, the feedback pin was number 1. We will click on it. The drain was pin number 4. The pin that was not connected was pin number 3. The DRV pin is not needed, and the VCC is already absent. Finally, we'll sort it out. We need to press the sort button. I'll click on it now. The system has displayed all the IC numbers that fall into this category. All the correct references are available here. If you remember, the same number, the TNY family, is also included here. As I showed you in the first method, clicking on the PDF for TNY274PN takes me directly to its datasheet page, where I can view its parameters. This picture shows all the parameters and differences between these ICs. Pause the video here to review all the differences. As I explained, the only significant difference is their wattage. All other parameters are the same for both ICs. That is the way you can identify the number of blown IC. Now, a significant amount of work has been done on this PCB, but its testing is still pending. Testing is crucial because we need to ensure that no other components are faulty. If we install the PCB without testing, it might fail again. In the next video, I'll show you the complete testing process to verify its functionality and confirm that the PCB is working perfectly. Click on the left or right thumbnail to watch our next videos, and subscribe. Thank you.